Hello everyone, and thanks for joining us today. We are Sumin and Kyulee from Yonsei University in Korea. Before we begin, we'd like to say that it's a real honor to present here. We truly appreciate the early stage work groups and the OHDSI community for this opportunity. So I'm Kyulee, and I'll briefly walk you through the motivation first, then pass it over to Sumin for the methods and results. This is the poster we presented at the symposium. So before we can do any multi-site imaging research, we need to make sure that different institutions actually perform the same exam. But in practice, exam names in EHRs are all over the place. Every hospital uses its own naming style, abbreviations vary, and even the order of attributes differs. So comparing exams across sites becomes extremely challenging. We do have terminologies like CPT-4 and SNOMED, but CPT is mainly for billing and SNOMED is general purpose. Neither really captures the detailed compositional structure needed to identify imaging exams correctly. Radiology exams are not just simple names. They are made up of modality, anatomy, contrast, view, and even clinical intent. A truly useful ontology has to represent these attributes explicitly. To address this, RSNA and LegendStrip created the Loink-Ladlex playbook. Ladlex is the standard vocabulary used in imaging reports, so it's very granular, including modality, anatomic location, contrast usage, and so on. And the Loink-Ladlex playbook combines those Ladlex attributes with Loink radiology exam identifiers to give a structured radiology-specific representation. Like RX norm composes ingredients and dose forms, the playbook composes modality, body region, view, and so on into a single standardized Loink radiology code. And you can see why this matters in the examples below. CPT takes liver and generalizes it to the broader category abdomen. And SNOMED keeps the anatomy but loses the contrast information. But the playbook keeps everything, the anatomy, modality, contrast, because each Loink radiology term is literally composed from small granular Ladlex pieces. So these are the part types, the Ladlex attributes used to define each playbook exam. But not all attributes matter equally. Modality, anatomic region, and contrast carry much more weight in defining an exam. So we need an ontology-based weighted approach. Even so, the playbook isn't widely used yet. Mapping is intrinsically difficult, very labor-intensive, and inconsistent even for experts. And the playbook itself is still young and updated frequently. So people have tried using LLMs for mapping, but radiology terms are too complex. LLMs hallucinate attributes, drop key information, and behave inconsistently. So an LLM-only approach just isn't safe or reliable. And that's why we developed ARKE, which views this as a knowledge encoding problem. ARKE combines ontology-based weighted matching to retrieve valid playbook candidates, and constrained LLM reasoning only for structured parsing and final selection. So the LLM never generates code on its own. It only works within the ontology structure. This turns local exam names into structural attributes, ontology concepts, standardized codes, and enabled consistent identification of heterogeneous imaging data across sites. I'll now hand it over to Sumin, who will explain our methods and results.
This slide shows the ARKE workflow. The input to the system is a local exam term, and the goal is to produce an output by mapping it to the correct Loink code. We first parse the local exam term using a Ladlex-based parsing approach. Then, using our custom rule-based algorithm, we generate the top 10 candidate Loink terms. This is the scoring-based retrieval step, which I will explain in more detail on the next slide. Finally, from these top 10 candidates, the LLM selector chooses the single most appropriate match. In this study, we used data from 2 tertiary hospitals, and we used the latest LOINC RSNA playbook as the mapping target vocabulary. ARKE consists of 2 parts, pre-processing and the mapping framework. We first use an LLM to structure local terms based on RADLEX part types. Then we perform ontology-based weighted matching using the knowledge graph, rule-based scoring, and RAG, and finally, the LLM selects the most appropriate playbook term. In pre-processing, our goal is to normalize each local term into a RADLEX-based JSON. We separate the cleaned exam name into the name field and map 18 RADLEX part types into the parts field. In step 1, we convert the entire playbook into a knowledge graph. Each LOINC code becomes a central entity linked to RADLEX attribute nodes, forming semantic connections defined by the playbook. In step 2, we compare the part type in the input JSON with playbook attributes and compute a weighted rule-based matching score. More important part types receive higher weights, making the final score more meaningful. Using these weighted matching scores, we rank all possible candidates and retrieve the top 10 highest scoring ones. Finally, the LLM performs constrained reasoning to select the best candidate. With controlled prompting, it captures clinical nuances while reducing hallucination. To evaluate our approach, a radiologist manually created the gold reference. We compared ARKE's retriever and final mapping performance with other retriever methods and direct LOINC mapping approaches. Here are the dataset characteristics. The 2 hospitals had slightly different modality and region distribution, allowing us to test cross-institution generalizability. This is ARKE's candidate retrieval results. Our approach achieved the highest hit rates and ranking scores across both test sets, consistently retrieving better candidates than other similarity-based methods. The final mapping accuracy was also highest with our pipeline, and the difference was statistically significant. This demonstrates that the constraint reasoning step of the LLM is reliable. Looking at the accuracy by attributes, modality and laterality showed strong agreement between the input and the final mapping. In contrast, anatomic accuracy was lower, likely due to greater variability in anatomical terminology. Some cases that looked misclassified actually contained richer details than the gold reference. Institutions can refine results by adjusting LLM reasoning prompts. In conclusion, ARKE enriches imaging data by fully leveraging the LOINC RSNA playbook, which is often underused. By converting local terms into structured semantic attributes and mapping them to the playbook, we move beyond simple mapping and capture the true meaning of each exam. Using these vocabularies within OMOP supports interoperable imaging across institutions, and the ontology-based approach may be useful beyond radiology. Multi-institution data contribution will further strengthen network studies and real-world evidence. Thank you for listening, and thank you to our collaborators and working groups for their support. If you have any questions or want to collaborate, feel free to contact us anytime. Thank you.